I'm Michael Condict. This is joint work that was done at NetApp by Fei Zhi, myself, and Sandip Shete. Fei is actually the primary author, but he decided he'd rather be with his wife and child, who are in China all this month, and I think he made the right decision. Okay, so what we're going to talk about is a technique for keeping track of an estimate of how much duplication there's in a volume without actually turning on the full mechanism of deduplication. For those of you who aren't familiar with it, deduplication just implies removing duplicates of the same block value or chunk of some size. It can be a fixed size block, or it can be a variable size entity, a sequence of data. And so you end up with only one copy of every unique value, and you save a lot of space. Sorry, I thought I was in the slideshow. I don't know what happened. Okay. Now, the problem is with deduplication, to do it just blindly, is that it usually saves space, but there's a hard-to-predict cost-benefit ratio. The amount of space reduction depends greatly on the type of data you have. If you have a volume full of compressed video, you won't get any benefit from deduplication unless there are exactly identical video files, because if there's any, if you just edit a video or a song file and change remove the first minute of it, after compression it will have no similarity with the original. There's also CPU and metadata overhead, and deduplication can lead to fragmentation. Obviously, if you have two files that share some blocks, you can't have both files be completely sequential on the disk because one of them is pointing to the blocks of the other. So this can lead to fragmentation and degrade read performance. So what we'd like to do is estimate the amount of duplication a customer can achieve before incurring the overhead of dedupe. And this isn't just for use by customers, but it would also be nice if the system could automatically turn on deduplication for volumes where it makes sense and avoid doing it for volumes where it doesn't. Now, the algorithm is not useful, an estimator is not useful if it takes as much space and or time as actually turning on deduplication. So the goals for this algorithm are that it should have a small memory footprint, ideally independent of the size of the volume, and have minimal compute overhead, ideally insignificant. And it needs to maintain an up-to-date estimate of duplication as the target data set changes. As writes happen, obviously the amount of duplication in the volume can change. And in order to be trusted, it has to provide some accuracy guarantees, even if only statistical guarantees. And then ideally, it should only have to look at a small subset of the data, so you don't have to scan the entire volume. Well, unfortunately, that last goal has been proven to be impossible. The work the area of trying to estimate duplication in a data volume is equivalent to a well-known research area in databases, which is to try to estimate the number of distinct volumes in a column of a database table. And in that rich area of research, there are proofs that any estimator of the amount of duplication, or conversely, equivalently, an estimate of the number of distinct values, if it looks at only a small sample, there are frequency distributions that make it very inaccurate. But we did achieve all the other goals. And we actually don't mind, we don't suffer much from having to look at all of the data, and we'll talk about why. So why is this last difficulty, why does it exist? Why is estimating duplication hard? Why can't you just take a small random sample, and if it's got, say, 20% duplication in it, then you can guess that that's the duplication in the whole volume? Well, look at these two distinct frequency distributions. Suppose you have one volume that has 50% blocks that are all 0 in it, and all the other blocks are unique. And then you have another volume that has 2 copies of each block. Maybe it's 2 copies of a large MPEG video. So in the first case, a small sample will show you instantly that 50% of the blocks are duplicates and nothing else is. And so a small sample will successfully estimate very accurately that you have 50% duplication. In the second case, the amount of duplication you'll find in your sample, and you can prove this mathematically, will be 1/2 times the sample percentage. So if your sample percentage is 5%, you will see 2.5% duplication. If your sample percent is 50%, you'll see 25% duplication. And you will have no idea what the right answer is, because just because you see two copies of lots of values doesn't mean you know how many there are. There might be 3, there might be 5, there might be 7. There just happens to be 2 in your sample. And there's a lot more that goes into the difficulty of estimating from random samples than this, but this is just a simplest example I could come up with to show why it's hard. Okay, so we have to look at every block in the volume, but we don't have to look at blocks repeatedly. So let's think about it. Let's just first talk about an algorithm for how to do this, and we can later show why it's sufficient. So what we need to do is chunk all of the data into fixed or variable size blocks. It doesn't matter which, and then we hash the contents of each block to a fingerprint. Fortunately, a lot of systems are doing this anyway. The fingerprint that we chose to use in our implementation was the checksum that's computed already by the storage system for data integrity checking. And then what we do is, if the fingerprint mod m has a certain value, let's say x, a constant value, we add it to our sample. So we're looking at every block, but we're only adding the ones to our sample that pass this filter. The reason this works is if the fingerprint produces uniform random numbers, then and we're only looking at the ones that have the value x. Let's let x be 0 for simplicity. The ones that are 0 mod m, then because of the uniform random nature of the hash output, we can expect that 1 over m of the distinct values are going into our sample. Okay, and we're deduplicating the sample as we collect it. So all we need to do is, at the end of running this algorithm, is multiply the number of distinct elements we found in our sample by m, and that's a good estimate of the number in the total volume. Moreover, if the hash is uniform random, we know the statistics of the error on this estimate. We know that the mean we know that the error has no bias. The estimate has no bias, and we know that it follows a normal distribution. The number of distinct elements for which mod m will be equal 0 is approximately 1 over m, but it follows a normal distribution. So we can give good error guarantees. And the graphics there are just showing the flow chart of what we're doing. But basically, we just, the reason to use 0 as the mod you're looking for is because you can just quickly check whether the low order, and m should be a power of 2 for efficiency, so that you can check whether the low order k bits of the hash are 0, and if so, you process them in the sample. Okay, we actually implemented this in a NetApp storage server to measure its performance. And the cool thing was that we could reuse almost all of the code of the existing deduplication algorithm that was already in place. All we do is filter it through this this mod filter that reduces the size of the deduplication metadata by a great amount. So I won't go through this in detail, but the green boxes are showing what happens once for the volume. You have to gather the fingerprints for every block on the volume, and that goes into a fingerprint database that's stored on disk. And as writes are happening, in line with the writes, we're creating a change log that indicates the new fingerprints of newly written blocks. And every so often, at waffle consistency points, when writes are updated on the disk, we merge the new fingerprints with the old fingerprints, and there's also a process of cleaning that has to get rid of obsolete fingerprints. And the net result is that at all times we have an up-to-date fingerprint database that is a small sample of all the fingerprints. It's the ones that pass the filter. This is just showing that our implementation is correct in that the errors that we get in our estimator are roughly the same as predicted by theory. As you make m larger, that we call it the filter divisor. As you increase the size of the filter divisor, your sample gets smaller and your error goes up. But in all cases with different sizes of the filter, our implementation matches the expected error characteristics for standard deviation of error, and there's no bias. This is the more interesting chart. It shows that what we're seeing here is how the error changes. The error are the green boxes at the bottom, and they are measured on the right axis. And the other dots are their values are expressed on the left vertical axis. And what this shows is, as a volume is written, the sample size keeps growing as you use a certain filter divisor. For instance, we started with a filter divisor of 4096. When the sample size gets above the size necessary for maintaining a certain error, we double or increase the filter divisor, and then the samples, and we throw out the ones that no longer pass the filter, and the sample size immediately drops from about 2,500 to from about 3,500 to less than 2,500 in the sample, and we keep doing that as the volume grows. We keep increasing the filter divisor. But the important thing to note about here is that the number of things in the sample is always between about 1,500 and 3,500, and the error remains below 5%. The size of the sample necessary to achieve a 5% error, or to achieve any given error, is independent of the volume size. That's a nice property. This is just a performance evaluation showing that there is very small effect on CPU usage and IOPS. This is a CDF chart of a large number of runs, and we can see that so the base case is slightly farther to the left. So there is a little CPU overhead in using various target sample sizes, but it's very small. And same for the IOPS. The IOPS are actually, for some reason, the larger is to the right. Yes. So we lose a little bit on IOPS, but it's less than a few percent. The latency, there's no significant effect on latency in this algorithm. So basically, the only work we're adding to inline writes is to take the checksum that the system already computed for consistency and seeing whether it passes the filter. And if it does pass the filter, we add that newly written block to our sample. And if our sample is getting too large, we increase the filter divisor. That's the only work to be done inline. So that explains why there's no effect on latency or IOPS, no significant effect. So in conclusion, yes, we can implement an efficient estimator of deduplication with statistical guarantees on its accuracy. The required sample size for a given relative error is small and independent of the volume size. One of the insights that we realized in that is that it's small and independent of the volume size for the same reason as the polling theorem says, that you only need to poll a certain number of people independent of the size of the population to get a certain accuracy in your poll results. The math is closely related. And we can keep an up-to-date sample in line with writes without incurring excessive overhead. The one application for this is to decide which volumes it makes sense to turn on duplication for, to do it either automatically or at the customer's request. And so that's all I have. I'll take questions now. Thank you.
All right, Kai Shen from University of Rochester. It's very interesting work, but I must have missed something, because if you do the content-based filtering, just look at the two examples you gave earlier in your talk. One example was that you have half the blocks to have the same content, right? So if you do content-based filtering, you either lose that block completely, or you just have it included. But in either case, I guess the first case is even worse. But you're going to have a very I must have missed something, because
no, you missed the same thing everybody missed, including me. Everyone asks the same question when they first hear about the technique. The thing you need to realize is we're not We don't care about the frequency of occurrence of any block. That's totally irrelevant to this algorithm. We are looking at every distinct value and only counting the distinct values that pass the filter. So it doesn't matter whether the 0 block, the one that is half the volume, it doesn't matter whether the block of all zeros ends up in our filter or not. It is just one distinct value. It doesn't affect the accuracy.
You know what? It makes sense. Thank you. Yeah.
Good question. I had the same question when I was first exposed to this algorithm. Okay, thank you.